we recognize a vertical expansion as happening when the graph stretches in the vertical direction, or the y direction, rising or dropping more quickly. A vertical compression, on the other hand, has the graph being squashed in the vertical or y direction, rising or dropping more gradually. In equation form, we recognize a vertical expansion or compression by noting the multiplier beside the y, or, more commonly, as a coefficient on the right side here. Whether it's a vertical expansion or a vertical compression simply depends on the number being multiplied. Just like we know that multiplying a number greater than 1 causes a bigger result, a coefficient that is greater than 1 tells us that it is being vertically expanded. And just like when we multiply a number between 0 and 1 causes a smaller result, we know that the coefficient that's between 0 and 1 will result in vertical compression. In the same way, if the graph is reflected vertically, we recognize a vertical expansion in the negative direction if the multiplier is less than 1. The vertical compression in the negative direction happens if the multiplier is between -1 and 0. Write the equation of the function shown in this graph. So we'll start by recognizing that this is a quadratic function, or degree 2. And we also see that it's reflected vertically. So let's put a negative out front here. Now we don't see any translations, either horizontal or vertical. That is, our vertex is right here on the origin, just like our base. So, are we done? Well, things look pretty good, except doesn't this graph seem skinnier than our standard quadratic? Well, let's see if this is true. Now, a standard quadratic would cross through 1, -1. That is, when x is 1, y would be 1 squared, or 1. And then with a negative, -1, so right here. Now our graph doesn't pass through this point, that is 1, -1. Instead, it passes through 1, -2 here. So yeah, our graph is definitely skinnier than our base quadratic. So our function drops more quickly, and we could say that it is expanded vertically, or expanded in the vertical direction. So to describe this vertical expansion, we could add a 2 to our equation as a multiplier out front here. The equation describing this graph would therefore be y equals -2x squared. And let's confirm this. When x is 0, y is still 0. When x is 1, now y is -2. When x is -1, y is also -2. They all fit well. The alternative equation format results from dividing both sides by -2, and we could have -1/2 y equals x squared. They're exactly the same relations, just a slightly different format. In this case, the -1/2 is with the y, which is kind of nice to identify it as a vertical expansion and reflection, both with the y being vertical. But this format isn't as common as just having the y by itself on the left. Now, if we were to look at our quadratic transformation in this format, that is y equals a x plus b squared plus c, we recognize that in this case, the b and the c, that are the translations, are 0. And the a would be our -2. The negative accounting for the vertical reflection, while the 2 accounts for the vertical expansion. Example 2. Write the equation of the function shown in this graph. Well, we start by recognizing this as a quadratic function again, or degree 2. No vertical reflection this time, and we don't see any translations, horizontal or vertical. That is, the vertex is right on the origin here, same as the base. So, are we done? Well, again, things look pretty good, except in this case, the graph seems wider than our standard quadratic, doesn't it? Let's see if this is true. Now, a standard quadratic would cross through 1, 1, as we know. That is, when x equals 1, y would be 1 squared or 1, right here. Instead, this graph passes through, well, a portion of 1. So, yeah, we definitely have something different going on. Let's try x equals 2. At x equals 2, the base quadratic would pass through, well, 2 squared or 4, right here. Instead, we're passing through 2, 1 here. So our graph is definitely a bit compressed from the base quadratic. We could say our function rises more gradually than the base, or we can say it is compressed vertically. To describe this vertical compression, we could add a 1/4 to our equation as the multiplier out front here. The equation describing the graph, therefore, would be 1/4 x squared. The alternative could be to multiply both sides by 4, and we'd have 4y equals x squared. Again, the same relationship, but in this case, the 4 is with the y, which is nice to identify it as the vertical compression. But again, not as common as having the y all by itself on the left. Now, if we were to look at our quadratic transformation here in this format, we'd recognize that the b and the c, the translations, would both be 0. And the a in this case would be our 1/4.